In this discussion, what is being asked is basically a general system with a lot of mass points m1, m2, until mn, and there are a lot of forces acting on all these mass points. So each point can have a external force that is acting on them. So they have a lot of external force acting on this system. And between all these points, there can be internal interactions, like mass point 2 can give a force F12. This is a force acting on 1 by 2. And then mass point 1 can also give a force back to F2, 1. So the thing is that Newton's third law tells me that a force acting on 1 by 2 should equal to the force acting on 2 by 1, but with a negative direction. So these two forces should be pointed in the opposite direction and with the same magnitude. So in general, Fij should equals minus Fji. Now, when we analyze this system, we can write down Newton's second law for each point. So the total force on mass point number 1 will be the external force on mass point 1 plus F12 plus F13 until the last mass point, which is F1n acting on mass point 1. So all this force is acting on mass point 1, and this will equal to the mass of the mass point 1 and times its acceleration. And we can write down the same thing for mass point 2. It will have an external force, which is not coming from the other mass point in the system. And there will be mass point 1 acting on it, and mass point 3 acting on it, until mass point n acting a force on mass point 2. And this will equal to the mass of mass point 2 times its acceleration. We can keep doing it until the last mass point, which will also have a external force on it in general, and all the other mass points can in general have a force acting on it, and we will keep adding until the minus 1 mass point. So what happens to all the mass points is like this. So the reason we study a bunch of mass points is because classically any system can be thought of as a bunch of mass points. A block is just a bunch of atoms which are mass points. A chicken is also a bunch of atoms which are also mass points. So when we study a system, we can in general think of a bunch of mass points interacting with each other and also getting forces outside of the system. So we can have So now what we're going to do is to sum every single equation on top of this. I'm going to add everything here. So on the right hand side, I'm going to get the sum of all the mass of each point times the acceleration. And on the left hand side, we will see that the force from 2 acting on 1 equals the minus of F on 2 plus 1. So when we sum them, these two terms will cancel each other. Similarly, when the mass on 1 on n will cancel mass on n on 1. And when we sum all the forces, every term here will be cancelled by one of other force. So at the end, we will get none of these forces, and what we get will just be the sum of external forces, which we call F external, or we can just say sum of all the external forces. Now, when we look at this term, it's usually meaningful to define a position called center of mass position. It is defined by summing all the positions of each mass point and divided by the total mass. So the importance of each point's position is weighted by their mass. So m here is the sum of all the mass in the system. What we can see is that if we divide RCM, if we differentiate it twice, m is a constant, all the mass of each mass point is constant. So what we will get is mass on the denominator times the sum of the acceleration of each point weighted by their mass. So we can replace the right-hand side of this equation as mass times the center of mass acceleration, because then this m here will cancel the 1 over m in the front of this thing, which is defined as the second time derivative of center of mass position. So we see that for a system, and it is a very general system because every system classically can be thought of as a collection of a bunch of mass points. What we have is the sum of external force acting on this system equals the total mass of this system times the center of mass acceleration. This is going to be very useful in today's discussion.